In the previous video, we took a long time to try to derive this idea of calculating flux, again, a special surface integral. We came up with the following definition as well as a simplification that would allow us to compute this integral for flux more simply if we had a parameterization for the surface we were talking about. All right, so let's take a look here at example number 1 to see how we can put this to use. Let's suppose that the surface that we're working with is a sphere, x squared plus y squared plus z squared is equal to 1. So notice that's a sphere with radius 1. I have it pictured down here. And let's suppose that f, my vector field, that represents again how the fluid is flowing. Again, I'm imagining that this sphere is going to be dunked into a liquid of fluid that has this sort of a motion to it. So notice here that the motion of the fluid is directly related to apparently the z-coordinate. So I can maybe start to imagine how the fluid's going to flow at a variety of points. At the point up here, where the z-coordinate is 1, the fluid's going to be flowing like this. Over here, where the z-coordinate might be, I don't know, a half, the fluid's going to flow like this. Over here, where the z-coordinate is 0, notice there's not going to be any fluid flow. And at spots with negative z's, my fluid's going to be flowing like this. So this represents the direction in which the fluid is flowing. But of course, we want to go ahead and think not just about that, but also about normal vectors that are going to exist to this surface. So we want to find the flux of F across this sigma in the positive direction. Now remember, the reason that we have to state something like a positive direction is because we're dealing with net fluid flow. If this thing is dunked into a tank of liquid, some liquid might seep in to this particular item, and some liquid might eventually seep out of the item, and what we want is a net. So if we took all the stuff that went out as maybe positive and all the stuff that went in as maybe negative, what would be the net total? Okay, so again, this idea of positive is helping us to understand that we need to orient. We need to think about which one of these directions are we going to consider as negative and which one are we going to consider positive. Now, since this is a closed surface that we talked about a couple videos back, we'll be able to say that the vectors that are normal to the surface and point outward are considered positive. So we're going to consider fluid that comes out of this particular surface here, comes out from within it or passes it through it in this direction, is considered positive flow, and anything that comes back into the surface or in through it, so anything that kind of starts here and goes toward the inside, is going to be considered negative flow. Okay, so with that in mind, let's go ahead and start to do some calculations here. The first thing that we might want to do is parameterize the surface, so that way we can easily go ahead and use our nice calculation that we had up here. Okay, so to parameterize it, we will use our knowledge of spherical coordinates to parameterize sigma. We actually did this in the last section, so I'm going to go ahead and kind of jot this down rather quickly. But you might recall that if I think about in spherical coordinates, I had already a relationship for what x was equal to, what y was equal to, and what z was equal to. And so I'm going to use that here, assuming that the value of rho, again, is going to be 1 in spherical coordinates. So notice here that if I kind of have rho as a 1, I can imagine setting up things in the following way. I would have, here I'm using u's and v's in place of thetas and phi's. Of course, if this is a little bit strange for you, don't worry, you can always just go ahead and switch back. So you can see here that I'm kind of using u in the role of, u is in the role of phi, and v here is kind of in the role of theta. So if I was to go ahead and set something up like this, no problem. Now I can just go ahead and calculate the cross product, do a dot product of that with my f, and then set up my corresponding double integral. Now here I'm probably going to go ahead and need to verify that, again, if u is playing the role of phi, it's going to range from 0 to pi, because again I want to start by looking up and then rotate pi to look down. And v is going to be playing the role of theta, so that's going to be from 0 to 2 pi. So here's a nice parameterization. So if I want to go ahead, and let me move this down here a little bit so I have some more space, but if I have my partial with respect to u crossed with my partial with respect to v, let's see what we come up with. Partials with respect to u, I'm going to have cosine u, cosine v. I'm going to have, cosine u sine v. And then finally, over at the back, I'm just going to have a negative sine u. If I go and do my partials with respect to v, I'm going to have a negative sine u sine v. I'll have a sine u cosine v, and then I'm going to have a 0, putting in my I, j, and k, and then I'm ready to actually compute this. Let's see what we come up with. So let's see, I'm going to end up with, it looks like, a sine squared of u cosine of v. Middle term is going to be a negative sine squared of u sine of v. Oh, wait a minute, not a negative, because it's already subtracted, so that's going to be positive sine squared u sine v. And then for my last term here, let's see, I'm going to get a cosine u sine u cosine v squared, and then that's going to be plus a sine u cosine u sine v squared. And you might see very similar to what we saw in the last section, which is that I'm actually going to end up with a cosine of v squared plus a sine of v squared once I do some factoring. And I think I can just simplify all the way down to this. Now, if you don't fully see that, I'd ask you to just, go ahead, pause the video, write out all the detail, make sure you can follow this. But for the moment, I'm just going to try to skip through some of those individual steps in efforts to try to compute this integral a bit faster. Okay, so since I have this now, it should be pretty easy to go ahead and say, I just need to take what I have here, and I need to dot it with f to set up my double integral. Okay, so my double integral over sigma for f dot n ds, which simplifies down to my f dotted with my cross product, ru cross rv, times my dA, which is in terms of u's and v's. So this would be double integral. My f is going to be 0, comma 0, comma, well, let's see, z. Well, I want to go ahead and update this value of z that's listed here with what I already have down here. So instead of putting z, I'm going to put what z represents in my parameterization, which in this case is a cosine of u. So I'm going to have a cosine of u, there's my f, and I need to dot that with my sine squared u cosine v sine squared u sine v. I'm going to really squeeze this in here. Sine u cosine u. Okay, so I have that, and then of course at the back I'm going to have my dA. I'm going to put my d here. Now, this dot product here is unbelievably simple because notice most of the stuff here is 0. So when I do the dot product, I'm really just going to have this cosine u multiplied over here. And so I'm going to have a sine of u, and then a cosine squared of u, and maybe I'll do something like a du dv. And so that means that if I can think about my bounds on u and v, I have this integral pretty much set up. So I can go, u goes from 0 to pi, and v went from 0 to 2 pi. So this is it. I'm pretty much done. Notice that this is actually really easy to go ahead and even do antiderivatives with. Notice here that I believe, you could double check me, but I think that the antiderivative with respect to u of what I have on the inside here is actually just a 1/3 cosine to the third of u. Checking with the derivative, the 3 would come down, lower this to a cosine squared, and then the derivative of the cosine would be negative sine, which I almost have. So if I just put an extra negative on here, I have a perfect antiderivative. I would just evaluate this from 0 to pi, and then I have dv. So let's see. This would be, if I plug in pi, I'm going to get cosine of pi is -1. -1 to the third power is -1. So this is going to get me 1/3. If I plug in 0, I'm going to get 1, and I'm going to get -1/3. So minus -1/3 there is going to get me this, dv. And so I'm going to end up with, this is going to be 2/3 v evaluated from 0 to 2 pi, and so I end up with a total value of 4 pi over 3. So if I think about again what this means, and that's very important to be able to do, what did we just calculate here? We said that if I submerged this surface into some sort of, say, a tank of liquid that was moving in this direction, where the fluid is flowing in this direction, then it would be the case that in a single unit of time, whatever we were measuring that time in, whatever the vector field is measuring that flow in, we would have 4 pi over 3 volume, units of volume, moving out of this particular sphere, or moving past the sphere in this direction as a net total. Okay, so this is an example of how we would actually go ahead and compute this concept of flux. And what again we're seeing is that, much like in the last section, it becomes a lot easier to go ahead and convert things over to a parametric form, so that way we can go ahead and use this simple equation to make our calculation with. In the next video, we'll take a look at another very similar example.